Okay, we are on the last section or the last part. I've made it a five-part video on chapter 8 of conceptual physics, and we're going to talk about angular momentum. Um, and so I don't interfere, let me dismiss my image. The inertia of rotation of rotating objects is called angular momentum. This is analogous to inertia of motion, which is momentum. Angular momentum equals rotational inertia times angular velocity. I times omega, I omega. This is analogous to linear momentum, which is mass times velocity. The rotational inertia is the mass distribution on an object, and the angular velocity is similar to velocity. Okay. For an object that is small compared with the radial distance to its axis, magnitude of angular momentum is equal to the mass times the tangential speed times the radius. The mass of the object times its tangential speed times the radius, which is analogous to the magnitude of linear momentum, which is mass times speed. Example, a whirling ball at the end of a string, a planet revolving around the sun. They both have angular momentum. If you've ever played tetherball, you know that if you were to hit it and it wraps around the pole, as it continues to wrap around the pole, it speeds up, and that's a conservation of angular momentum. Now, we'll get to that. An external net torque is required to change the angular momentum of an object. Rotational version of Newton's first law is an object or system of objects will maintain its angular momentum unless acted upon by an external net torque. Okay, an object or system of objects will maintain its angular momentum unless acted upon by an external net torque. Okay, suppose you are swirling a can around and suddenly decide to pull the rope in halfway. By what factor would the speed of the can change? So you're reducing the radius by half. So would it double in speed, 4 times the speed, half the speed, or 1/4? I would say it would double in speed. Let's see if I'm right. Yes, it doubles in speed. Angular momentum equals mass times the tangential speed times the radius. I think they need a little X in there. They forgot it. I'll try to correct it on the handouts. Angular momentum is proportional to the radius of the turn. No external torque acts with the inward pull, so angular momentum is conserved. Half radius means the speed doubles. Okay, the law of conservation of angular momentum states that if no external net torque acts on the rotating system, the angular momentum of that system remains constant. This is analogous to the law of conservation of linear momentum. If no external force acts on the system, the total linear momentum of that system remains constant. And you can look up examples. If you say conservation of angular momentums, skater, you'll see ice skaters that are spinning slowly, and as they move, they're changing their moment of inertia, their rotational inertia, by pulling their arms and legs in towards them. They're changing their mass distribution, and they speed up. And there's a little cartoon version of that here. Example, when the man pulls the weights inward, his rotational speed increases. I have a video of me demonstrating this. It's not as dramatic as this little cartoon shows, but you can see that I speed up a bit when I pull the weights in. They're 2 kilogram weights in each hand. Anyway, I want you to notice this little equation. When his arms are spread out, his rotational inertia is large. and his rotational inertia is large, his angular momentum is small. When he pulls his arms in, he decreases his uh, rotational inertia, and the rotational angular velocity increases. So you can see big I little omega is equal to little I big omega. So if you decrease your rotational inertia, you're going to increase your angular momentum. Um, okay, suppose by pulling the weights inward, the rotational inertia of the man reduces to half its value. By what factor would his angular velocity change? Well, if you look, there's no square term. There's no so it would be proportional. If it's half its value, he's going to double his rotational inertia. Um, if you have the rotational inertia to keep the angular momentum constant, the angular velocity doubles. Okay. And that's it. That's it. I encourage you, I may post some on Canvas, but I encourage you to just look up angular momentum of a skater or something like that. You'll find YouTube videos that show that. Okay, that's the end of chapter 8.